We present the example to Problem 2, which appeared on Exam 3 in fall 2014. I'll start out by saying this is a Moore's circle problem. Students didn't find it particularly difficult, but there's a lot of steps and a lot of things that we ask for. Many students lost points for not answering every single thing that we asked for in the problem. So the best thing to do on a problem like this is to make sure you reread after you're done and make sure you've addressed everything. Problem statement reads, consider the plane stresses shown on the differential element, that's this guy right here, with respect to the xy plane and associated Moore's circle. Here's the stress element. We could interpret this as sigma x equal to negative 21.5 KSI. Sigma y, also acting inward, as negative 18.5 KSI. And the shear stress, tau, xy, equals positive 11.9 KSI. If I look at those points on Moore's circle, sigma x, negative 21, should be paired with negative xy. Oops, the point is labeled wrong. We identified that during the exam, and hopefully it didn't trip anyone up. Those are the 2 points on Moore's circle. Okay, part A asks, compute the normal stresses sigma n and sigma t that act on an element rotated 40 degrees from the xy axes. The element rotation is 40 degrees. That corresponds to 80 degrees on Moore's circle. To solve for the values precisely, we use the stress transformation equations. Sigma n equals sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 times cosine of 2 theta plus tau xy times sine of 2 theta. This is what a lot of you like to call plug and chug. Put the values in, negative 21.5 minus 18.5 over 2 plus negative 21.5 plus 18.5 over 2. Have to be very careful with signs. Cosine of 80 degrees plus the 11.9 times a sine of 80 degrees. That computes to negative 8.5 KSI for sigma n. We can find sigma t a little bit more easily from the relation that sigma t equals sigma x plus sigma y minus sigma n. So that would be negative 21.5 minus 18.5 minus a negative, so plus 8.5, which reduces to negative 31.5 KSI for sigma t. Notice we did not ask you to compute tau, just trying to save you a little time there. The next part, I locate these points approximately on Moore's circle. This is kind of a check for your calculation to make sure the value is right. So what I'm going to do is I'm going to go positive 80 degrees to theta on Moore's circle from my original points and find those points, and that's where I think sigma n should be. Sigma n of negative 8.5 KSI and sigma t over here of a negative 31.5 KSI. I look at my points by inspection. Their values on Moore's circle is approximately what I computed over here. So I think I didn't make an error and can proceed. Part B, compute the principal stresses and the maximum in-plane shear stress. Identify those on Moore's circle as well. For principal stresses, we need to compute the center of the circle, sigma x plus sigma y over 2, which is negative 21.5 minus 18.5 over 2, which is going to compute to a nice negative 20. The radius, square root of sigma x minus sigma y over 2 squared plus tau xy squared, and that is equal to, come down here, negative 21.5 plus 18.5 over 2 squared plus 11.9 squared, and that gives me radius of 12. Another nice number. going to go ahead and skip to a new sheet. Okay, remember we just computed A equals 12, or sorry, A equals negative 20 and R equals 12. My principal stresses, sigma P1 is A plus R, is equal to negative 20 plus 12, which is negative 8 KSI, and sigma P2 is equal to A minus R, or negative 20 minus 12, or negative 32 KSI. I'll locate those on my circle. There's sigma P1 equals negative 8. Sigma P2 equals negative 32. They look right. Tau max is equal to the radius is equal to 12, or 12 KSI. I'll label that on the circle. Come right up here. Tau max equals 12. Okay, I want to make sure I circle those answers and make them nice and visible. Okay, I did everything in part B. Part C, compute the angle of rotation theta p the element must undergo to get from the xy axis to the principal axis. Is, this should be theta p, is it positive or negative? We use this formula to compute the value of theta p, 1/2 inverse sine of tau xy over r. There's an alternative formula, but I believe this one's the easiest. Inverse sine of 11.9 divided by 12. This gives you a value of 41.3 degrees. Okay? To figure out the sine, I'm going to go from this stage down to the closest direction to the principal axis. That's 2 theta. I believe that is about, this should say 41.3. I believe that's about 82 degrees, so I think I've done it correctly. And the rotation is in the clockwise direction, which is negative. So theta p equals negative 41.3 degrees, negative by inspection. Okay, part D. What is the absolute maximum shear stress in the material? Does the maximum occur in plane or out of plane? So we need to consider what is the third principal stress and evaluate the maximum shear based on that. For plane stress situation, we know that a third principal stress is located right over here at 0. So sigma P3 equals 0. I can evaluate the absolute maximum shear stress as sigma P1 minus sigma P3 over 2, where I want to reorder or make sure I order the principal stresses so that sigma P1 is the largest and sigma P3 is the smallest. So the largest here is 0, actually, and the smallest is negative 32. Divide by 2, and that gives me a value of tau max equals 16 KSI. Okay, that's larger than what I observe in this Morse circle, and that's because I can draw a larger Morse circle for our rotation about the 2-axis, which looks like this. Okay, and it will have the value of the maximum, maybe I'll draw it down here, the maximum shear at about 16 KSI. So that is the absolute maximum shear, and it is not in the original circle, so it is out of plane. Okay? If my original circle crossed the tau axis, then the maximum shear would occur in plane. That completes this problem.